Okay, so we're going to talk about how to evaluate iterated integrals. And the first thing that kind of leads into this is what we call Fubini's theorem. Fubini's theorem is kind of it's like the integral counterpart for Clairaut's theorem, the one that says that when you're taking mixed partial derivatives with respect to both variables in a two-variable function, the order of differentiation doesn't matter. So if you differentiate with respect to x first, and then with respect to y, or if you reverse the order and integrate with respect to y first, and then with respect to x, under the right conditions, you get the same mixed partial either way. So Fubini's theorem is kind of similar, and basically what it says, first of all, is if we're evaluating a double integral over some rectangular region R of a multivariable function f of x, y, dA, we can express that or evaluate it as an iterated integral. And notice that there's two different ways of expressing that here, where the dy comes first followed by the dx, or where the dx comes first followed by the dy. Now remember, the innermost integral is the one you evaluate first. So in this case, the integral from c to d of f of x, y, dy, treat that as a single or like a partial integral that we integrate only with respect to y, and then the result is likely to look like a function of x. So that gets passed along to the next integral out here, which we integrate with respect to x. However, if we reverse the order, if we wanted to integrate with respect to x first, and then obtain a function of y, or a function in terms of y, which gets passed along to the outer integral, we can do that as well. But notice that if we switch the order of integration, so dy first, followed by dx, or dx first followed by dy, we also have to adjust where the limits of integration appear. So this c and d, remember, that corresponds to an interval on the y-axis. So these are treated as y values, a and b are treated as x values. They should correspond to whatever variable we're integrating with respect to. So Fubini's theorem says that the order doesn't matter as long as we make the necessary adjustments here. Under some assumptions, f has to be continuous on that rectangle R, you'll notice here there's a more general set of assumptions we can make where it doesn't actually have to be continuous. It can have a finite number of discontinuities, but we're not going to really need that assumption for the examples that we do. So we're not going to prove Fubini's theorem. It's actually a very difficult and complicated proof. It's beyond the scope of this course, but we can kind of visually see why it's true for the cases where f of x, y is a positive function. So here's that image we looked at before where we're talking about this solid, this blue solid, and we determined its volume by looking at cross sections and their areas, and then using that formula from chapter 6. Here, this integral right here corresponds to this first integral, where the area of that cross section, a of x, is given by the inner integral here, the one with respect to y. And then when we use the outer integral, it's again like stacking up those cross sections to create a solid, which gives us a volume. But if we took the cross sections perpendicular to the y-axis instead of the x-axis, we would get something that looks like this. And in that case, because the curve up here is parallel to the xz plane, we think of that curve as really z as a function of x. So the dx is what's showing up here first. This inner integral is going to represent the area of that cross section, and then integrating with respect to y is what moves that cross section along the interval CD, giving us a volume. So in either case, whether we integrate with respect to y first or with respect to x first, those cross sections are still creating the same solid, so we should get the same volume from them, which is why we get this equality here. That's not a formal proof, but it's going to be enough for us to kind of have an intuitive idea of why this works. So let's move up to this example right here. So I'm going to evaluate this double integral. The function is y e to the x minus y dA, and the rectangle R is 0, 2, 0, 1. So according to Fubini's theorem, I can choose to integrate this with respect to x first or with respect to y first. It's kind of my choice, and in some cases, using one variable first will make the problem easier than if we did it the other direction. So looking at this function, if I were to integrate with respect to y first, then I would need integration by parts, because y times e to the x minus y looks like a function of y times another function of y, where x is held constant. However, if I integrate with respect to x first, then I don't need integration by parts for that first step. So that's going to make things a little easier. So let's see what this would look like if I integrate with respect to x first. The outer integral is the one I do last. So the outer integral should be using the bounds on my y, that's 0 to 1. The inner integral is going to use the 0, 2 interval, so that's 0, 2. Y e to the x minus y. And then the dA is going to change into either a dx dy or a dy dx. The first term is going to be whichever variable I'm using first, dx in this case. Okay? All right, so again, remember what this means. I'm evaluating this integral first as a single variable integral where y is held constant. So if y is held constant, this is just e to the y, a constant times e to the x minus a constant. It's its own antiderivative in this case. So my integral comes out to this, y e to the x minus y. And then we evaluate that from 0 to 2. There's my dy. Okay? Now if we were to evaluate this from 0 to 2, notice if I plug a 0 in, where these are x values, so this should all correspond to what I'm plugging in for only that x. The y's are considered constant here. Okay, so if I were to do this the way I do any definite integral, plug in the 2, and then subtract what I get from plugging in the 0, I'm going to end up with this integral here after some simplification. So I'm going to just go straight to what it looks like after simplifying. Y e to the negative y times e squared minus 1 dy. Okay, takes a little bit of work to get to this, but you should be able to fill in the gaps here. Okay, so now we need to do the integral with respect to y from 0 to 1. E squared minus 1 is a constant. We can bring that out of the integral, but what remains does require integration by parts. So we weren't able to escape parts completely, but at least we got to save it for last. So let's look at how we would do that. I'm going to set u equal to y. dv then would have to equal e to the negative y. And again, this e squared minus 1 is going to be brought out, so I don't need to use it anywhere in here. Du is going to be dy. One thing I did forget, I should include the dy here as well. V then would be negative e to the negative y. Okay, so using that to evaluate this integral, let's start by bringing the e squared minus 1 out. Okay, and then integration by parts says this is equal to uv, which is going to be negative y e to the negative y, evaluated from 0 to 1. Minus the integral from 0 to 1 of v du, negative e to the negative y dy. I'm going to take the negative from the v and bring it out to create a plus here, and then I can just call this e to the negative y dy. Okay? From here it's all just calculus 2 kind of stuff, so the e squared minus 1, still e squared minus 1. Here, if I plug a 1 in, I'm going to get negative e to the negative 1 power. If I plug a 0 in, the whole thing goes to 0. So this is going to give me negative e to the negative 1 there. Integrating this guy, I'm going to get plus negative e to the negative y from 0 to 1. Okay, and then after evaluating this part and simplifying things down as much as possible, you're going to end up with this answer, e squared minus 1 times 1 minus 2 e to the negative 1. Okay, you can fill in the gaps there, shouldn't be too hard. All right, so that is one example of evaluating a double integral.